Let me derive. This is our equation for buoyant force. Let me just show you where it comes from. Okay. Here's a diagram here. We've got a couple heights, right? We've got the top of this thing, which it's hard to see, but there's some area on the top of that, right? Understand that the force on the bottom is more. There's more pressure down here, and there's less pressure up here. Okay, so the forces of the water, the pressure force that's pushing to the right is canceled by a force to the left on this side, right? The horizontal forces all cancel out, but the up and down force doesn't cancel out. So if this is, say, a cylinder in there, right, there's more force up than there is down, right? And that's because there's less pressure on the top, more pressure on the bottom. So this causes a net force. So that force, that buoyant force, is just, in this case, F2 minus F1, right? F2 is going to be rho g H2 times the area, right? Right, because pressure times area is force, right? Okay, and then we're going to subtract from that rho GH1, which is the pressure up here, right, times that same area, and that'll give us our force, right? Okay, now if you look at this, you can end up writing it this way: rho G H2 minus H1 times the area, right? Well, H2 minus H1 is just this dimension right here, yeah? H2 minus H1 is just the height of the cylinder, right? So it's equal to, and then the height of the cylinder, this delta H, A times delta H is just the volume. So you end up with rho G times the volume, right? So this is the volume of the fluid displaced. That's the density of the fluid. And it just depends on the volume of it. And it even works, you can do the calculus on it, even works if this isn't a right cylinder and if it isn't oriented exactly that way. It just works. Okay, so this is our buoyant force, like that. Okay, let's do I've got some examples for you, by the way. Okay, so what is the buoyant force on a 3 centimeter diameter air bubble underwater? We know that these things move upwards, so there must be a force acting on that, right? So the buoyant force is going to be the density of the fluid, not the density of that air, right, times the volume displaced, right? The volume of the fluid displaced times G. And so the density of the water is 1,000 kilograms per cubic meter. Our volume displaced is going to be 4/3 times pi times, and then our radius is 0.015 meters, right? So be careful with your diameters here, right? And then that's to the third, right? So rho v, and then we're going to multiply by 9.81. Okay, so let's see if we can do this. 1,000 times 4 divided by 3 times pi times 0.015 to the third times 9.81. This is high stakes. Let's see if we can get the right answer here. And wow, what did I just do? Times 4 to the negative 51. This can't be right. Okay. I did something there at the end. Oh, all right. Okay. Must learn how to use calculator. Okay. After raising that to the third, I needed to go, okay, times. I'm too embarrassed to tell you what I just did. Okay, so this is 0.13. I forgot to hit the right arrow. You got to hit the right arrow and put that there. 0.0138685 newtons. Okay, so this is going to be newtons. How is it newtons? Let's see, this is going to be cubic meters, right? And then this is newtons per kilogram. So cubic meters cancels cubic meters, newtons per kilogram cancels, and you end up with newtons. All right, I've got it. All right. How about this one? Let's do one where we've got this iron shot. What is the buoyant force on this shot submerged in water, right? And then this looks like we can't solve this, right? Well, we can. Okay, the first thing we're going to do is we're going to find the volume of the shot, right? The volume is going to be the mass divided by the density. Okay, and I'm using density as mass over volume, right? So the volume of the shot I'll call it VS, is 5.45 kilograms. And then we need the density of iron, which is this 7.8 times 10 to the third. So this is 5.45 divided by 7.8 E3. And this is small, 6.987 times 10 to the minus 4 cubic meters. But remember, a cubic meter is an outrageously large. This is like 0.6 liters, if that helps. Okay. Okay, so let's see. What is the buoyant force? So now we can find the buoyant force. So let's do that. Okay, the buoyant force is the density of the fluid. So this is, it's submerged in water. So we got to use the fluid, right? Which is 1,000. So I'm doing this, right? The volume of the fluid displaced would be the same as the volume of the shot. This is Archimedes' principle. 6.987. All these great names, right? And then the G is just 9.81. Okay, so the buoyant force on this thing is 1,000 times that answer that I just got times 9.81. And I get that it's 6.85 newtons of buoyant force. So here it is under the water, right? Here's this steel shot, right? And there's a force of 6.85 newtons acting up. Okay. So what is the weight of the shot in the air? That's easy. Weight is mg, is 5.45 kilograms, right? Times 9.81 newtons per kilogram, by the way, are the units of that. All right, so 5.45 times 9.81 is 53.46. So here it is underwater, right? Let's draw another arrow down, not to scale. 53.4645 newtons, right? So this is gravity acting down. This is the buoyant force, right? This is gravity. And then it says, what is its apparent weight when it's submerged? Well, this is a weird thing, right? An object that's underwater will appear to weigh less, and that's because, of course, the force of gravity is canceled out by the buoyant force, right? And the closer it is to the density of the fluid, it's almost floating, right? So it's you can actually get very little apparent weight, right? So it's apparent weight submerged. The apparent force of gravity is just the difference between this. It's 53.4645 minus that 6.85. Okay, so minus 6.85 is 46.61 newtons. That's its apparent weight, right? So if you had a string, if I said I'm holding this by a string, that string would have a tension of 46.6 newtons on it, right? You could even set up like an equilibrium expression if you wanted to, if this common sense approach doesn't work. Where you just add up all these forces, right? This would be upward, this would be downward, right? And then this would have, you have to have a positive force like that to put this in equilibrium. Yeah, these are common problems.